Hello, dear viewers. Welcome to the world of mechanics. Here, if I draw a hoop, here's a hoop, and it's pulled by two strings in the opposite directions. And force in one string is 500 newtons, and the force in the other string is minus 300 newtons. What is the sum of the forces? Sum of these two forces? I mean, can I simply add them? Find the sum. If I say that 500 plus 300 is equal to 800, so is it 800 newtons? Or it depends on the direction of the two forces. I mean, if both forces are in the same direction, 500 and 300, their sum is, the effect is to reinforce each other. They will reinforce each other. But if they are in opposite direction, like this, and the angle between them is 180 degrees, they will cancel out the effect of each other. I mean, they will not support each other. They will resist each other. Same forces, but if we change the angle between them, the overall effect changes. And this is the core idea of today's lesson. We'll explore it. Stay with us. And we'll start from the basic. Because most of the students, they fear mechanics when they face complicated, complex, hard to understand formulas. They think it's unapproachable, inaccessible, impenetrable. And this fear actually stops them from deepening their knowledge and their understanding of this subject. And believe me, I'm not saying it as a hollow claim. No. If you try to see this subject from a different perspective, from a perspective of a practical mind, then you will be amazed by discovering that how easy it is actually to understand, and how close it is to our everyday life. We are actually half mechanics. We are actually, by nature, we are, you can say, experts of mechanics or practical users of mechanics. And we can understand it just by recalling where we applied it, where we applied the rules of mechanics, not knowing actually in words, in the language of mathematics, in a formal, rigorous language. But we do know it. So there is a wide gap between actually that discovery and the syllabus, the text. There's a wide gap, and we are to fill that gap. So we are actually standing in the middle of the way. So start from very basic concept of scalars and vectors. What is a scalar quantity? For example, if I write 10 kilogram or 5 seconds or 30 degrees centigrade or 200 joule or 750 kilogram per meter cube. In all these quantities, the numerical size and a unit, they completely describe the quantity. We don't need any direction. For example, 10 kilogram upwards, downwards, forward, backward. It doesn't make any sense. We never need it. So we describe it as a scalar quantity. And scalar quantity can be positive, it can be zero, it can be negative. Depending on the quantity and the baseline. For example, temperature can be -5 Kelvin. Oh, sorry. I mean, -5. Yeah, it can. It's another thing that -5 Kelvin is not accessible yet. -5 degrees centigrade. But it doesn't mean that -5 is some kind of direction. This minus sign indicates some kind of direction. No, it does not. It's actually the baseline. It's 0 degrees centigrade. So the temperatures below 0 degrees centigrade, they are negative. And the temperatures above it, they are positive. That's it. Now come to a different category of quantities. And those are quantities which ask for another thing, another detail. For example, if I say I am pulling a block with 500 Newton force, so 500 Newton force, okay, I'm applying this force on this block, but I'll find the mass. Immediately. In which direction? I mean to the right, to the left, upwards, or downwards. Am I giving you any new information? We are already using it. We know it. That force asks for another detail, another information, as necessary as the number itself of the unit. And that is direction. So I have to state for the complete description of force that I'm applying force on 30 degree angle. Okay, or I am applying force on -20 degree angle. It's 5 Newton force making an angle of -20 degree with the horizontal. And this is 30 Newton force. It's making an angle of 30 degree with the horizontal. So this direction, it's very important. And one thing was magnitude. It's equally important for scalars and vectors. Second one is direction in case of vectors. And the third one is, oh, okay, if I just change a little thing here, a little component of this detail, like here, if I have this one, where you put the arrowhead, the line of action. This is the line of action of force. If I just change the arrowhead, the direction of the arrowhead, what will happen? Everything else is the same, angle is the same, line of action is the same. I mean, the force is acting along the same line, but the effect is completely different. That is what sense. So in vector quantities, especially in forces, sense is also important. So there are three things: magnitude, direction, and sense. And if you want to include the fourth thing in case of forces, that's called line of action. Line of action. This line along which the force is acting. Call it line of action. That's it. Now we come to a design problem that a 500 Newton force is being applied in the center of the door. If here is a door, and I'm applying the force here in the center, and the same force applied at the handle, and they have same description, same magnitude, but their effect is quite different. They do not produce the same rotational effect about the hinges. These are the hinges. One force is acting here. The second force is acting here. So these two forces are producing a completely different effect. So it means that in mechanics, actually, we consider force, the magnitude of the force, its direction, and the line of action. And the line of action. For example, here's a point, and the body, it's a rod, and I applied force here. If applied in this direction, it will rotate it. We don't need theory of mechanics to see that it will rotate it. This force will rotate it. But if I apply the force in this direction, what will happen? Will it rotate it? Can it rotate it if it passes through the center? Through the center. And if I change the angle like this, now there is a perpendicular distance. And this is the line of action of the force. And this force is not passing through, this line of action is not passing through the center. Don't go deep into geometry or lines or perpendicular distances. No, just ask yourself, imagine that if I apply force in this direction, Will it rotate the door? Will it rotate this object around this center or not? Some part of the force will rotate. Some part of the force will pass through the center. Some part will rotate it. Or roughly we can say that yes, it will rotate. But this one, this force, it will not rotate. It will never rotate. Because it is directly passing through the center. Yes. So how important is the detail of the force, its magnitude, its direction, its sense, and line of action. They are equally important. For example, here, if I apply a force on this end of the object, it will push the object. If I maintain the same line of action and apply the force here, the same force, same sense, same direction, and the line of action is even the same. Well, the point of application is different. So in this case, we'll say that the force is pulling the object. So point of application is also important. I'll not go into detail of all these things here. I'm just introducing you to different aspects of forces. How we're just exploring it together. There's different aspects, different sides of an object, and the object is force. Nothing to fear about. Nothing. Very slowly, gradually, we'll move into it, and we will work on the forces to see how forces work on the objects and to see the inner beauty of the subject that is actually eclipsed by the equations and by mathematics, by calculations, very raw, boring, and silent calculations. Actually, everything, every step in mechanics actually speak. Every step speaks. It tells us something. And when we start knowing the language, mechanics, the language of each step, we start taking interest. Interest will build up automatically. You don't need to force it. Now comes scalar multiplication of vector. I mean, if I have 5 Newton force here, and the force is F, and we say it's a vector, therefore I'll draw this arrowhead over this letter F, just to show that it's a vector. So what's twice this force? I mean, if here, how to draw the force? 5 Newton. If every Newton is equal to 1 centimeter, then 5 Newton is equal to 5 centimeters. I need to draw 5 centimeter long line. 1 centimeter, 2, 3, 4, and 5. Okay. So here I will draw. It's 5 centimeter long. 5 centimeter long vector. The length of this vector shows the magnitude of the force. It's 5 Newton. if I multiply the 5 Newton force by 2, it'll become 2 times F is equal to 2 into 5 Newton. That is equal to 10 Newton. Okay, so 10 Newton. If 5 Newton is equal to 5 centimeter according to my scale, 10 Newton is equal to 10 centimeter. So it's 10 Newton. That is equal to 10 centimeter long line. It's a vectorial representation. How to represent it? As a line with an arrowhead on the end. And here, the point is that its line of action is not changing. The same line of action. Sense is not changing. Only magnitude is changed. And direction is the same. Direction makes unchanged. What if I multiplied by a negative? I mean, minus 1f. Or we can say minus 2f. So it's 5 Newton minus 2f. It means I will multiply by 2. Okay, if I multiplied by minus into 5 Newton, it's equal to minus 10 Newton. So it will be in the opposite direction. It will be in the opposite direction. Minus 10 Newton. Actually, the power is off in the background, but it shouldn't disturb the quality of the lesson. So stay in contact. We'll complete it in time. Okay. So when I multiply it by a negative number, it becomes minus 10. And what difference does it make? It actually changes the direction. Now the direction is opposite. So minus 10 Newton is opposite to 10 Newton. So it's like that. If I'm pulling this object with the 10 Newton here and minus 10 Newton here, we don't need algebra. We don't need algebra, actually, to conclude that the object will remain on the same spot. It will not displace. Why? Because it is being pulled by 2 opposite forces. It is being pulled by 2 opposite forces. And that's why the sum is, the resultant is 0. No effect. 0 Newton. They are canceling out each other. So we can say that if we have a pair of forces like F1 is equal to this and F2 is equal to 300 Newton and they are in the same direction, they will reinforce each other. So the resultant is equal to 700 Newton. And if one force is 400 Newton and the second one is minus 300 Newton, what will happen? In the opposite direction? And in my lessons, try to Imagine, try to think this thing in a physical sense. 400 Newton in this direction, and 300 Newton in this direction. It's negative. So if this direction is positive, in our convention, the right direction is positive, then the opposite of the left direction will be negative. So it's 300 Newton. So what's the resultant? We call it FR. That is equal to what? No need of algebra. No need of it. He is actually exactly 400 Newton. So out of it, 300 Newton is used to overcome or balance or cancel whatever word you might use. Don't go into technicalities. This 300 Newton on this side, it is canceling the 300 Newton on the other side. And that's it. Zero balance. I'm giving you something. You're giving it. You're paying me back. You're giving me back. Zero balance. I mean, we can say that there's no net effect. Okay. Net effect is zero. 300 Newton and 300 Newton. Cancel out each other. What's left? Only 100 Newton this side. On the right side, that is left. So this 100 Newton is actually the real force, the net. It's a saving. So if another body, another person is pulling the same object in the same direction with 100 Newton force, actually both are doing the same thing. We can say that in terms of forces, the overall effect of the force is the same, provided the direction and line of action and sense don't change. So this is what we call the resultant, the effect, the ultimate effect of the two forces. Sometimes we call it a force system. When a object is under the effect of more than one forces, we call it a force system. So here the force system, actually, it is reduced to a single force. That is the effective force, the real effective force. And that is 100 Newton. But what happens when one force is in this direction and the second one is in this direction? And they have an angle of 90 degrees with each other. Unlike the angle of 180 degrees in this case. What happens? Let's say we call it F1, we call it F2. It's 400 Newton. This one is 300 Newton. Now, if we add them, we add these forces. F1 in this direction and F2 in this direction. They're making two sides of a right angle triangle. I mean, one force is pulling the object in the horizontal direction in the right, and the other one is pulling the object in this direction. So the net effect, if we imagine it, try to imagine it, that the body will move. If body is allowed to move, it'll move in this way. At the same time, it'll move to the right and upward. Right, upward, right, upward. So this kind of path, it will take this kind of path. Most probably it will take this kind of path. It means that if I remove all these two forces and I apply only one single force in this direction, somewhere in this direction. I don't know the angle yet, but I know that if I remove these two forces and apply just like this man, apply a single force, because I want a very simplified approach. I want single force having the same effect on the body. So this force will work. This force will move this body in the same direction. It may be curved, it may be aligned. I don't know, but it will be in this direction, not in this direction. I mean, if I say no, it will be in this direction, or in this direction, or in this direction, in this direction. What will you say? You will reject all these because these two forces will not move the body in this way or in this way. Okay, these two forces will not in this way or in this or in this. No. So the net effect is this. This is called result. And it's a right angle triangle. And we can easily find the length of this side. If we have the lengths of these two components, we call them components of the force. These are the component forces. And finally, we remove these two forces here. And this force alone, this force, it will work the same way these two forces are doing. That's it. We call it a result of force. We'll go into more detail in the next lesson. We'll continue right from here. So today we learned that how to find the sum of forces and what components are important for the forces to describe the force completely. And we did it without the involvement of heavy mathematics. Obviously, the numbers should be there like this, but we didn't use any geometry, any lengthy geometry or trigonometry or algebra. We actually all these subjects are actually companions. They're not our opponents. They're companions to assist us, to help us, to understand, to analyze, to solve the problems of mechanics. But the main thing is the involvement of imagination. How we already do it practically. Nothing in this lesson is new for us in the terms of practical applications. We are already doing it. Even a boy of 10 years is already doing it. Nothing new. Just make your mind and continue with us. We'll explore this world of mechanics right from the basics to the advanced level. Thank you for your time, for your focus. We'll meet soon. Bye.